This is the video that's going to cover section 2.7, which is on the measures of the spread of the data. So we've been talking about measures of the center of data and location of data, and now we're going to talk about how spread out our data is. So a little vocab review. The range is the difference between the largest and the smallest values of a data distribution. So you would take max minus min to get your range. X bar is our sample mean, so it's the average or mean of our sample. Mu is the population mean. So the standard deviation. So an important characteristic of any data, any set of data, is the variation in the data, how much it varies from each other. It's the amount of dispersion or scattering of values from a central point. So in some data sets, the data values are concentrated closely near the mean, and in other data sets, the data values are more widely spread out from the mean. So the most common measure of variation or spread is the standard deviation. And the standard deviation is a number that measures how far data values are from their mean. In general, how far the data deviates from the mean, which is that measure of center. So the standard deviation provides a numerical measure of the overall amount of variation in a data set. It can be used to determine whether a particular data value is close to or far away from our mean. The standard deviation is always positive or zero. So as we're going through the calculations we're going to see in this video, if you get a negative number, just know you've done something wrong. The standard deviation is small when the data are all concentrated close to the mean, exhibiting very little variation or spread. But the standard deviation is larger when the data values are more spread out from the mean, showing more variation in the data. So an example of this, supermarket wait times. Suppose we're studying the amount of time that customers wait in the checkout line at two supermarkets, Supermarket A and Supermarket B. The average wait time at both supermarkets is 5 minutes. So that's the mean for both of those data sets. And at Supermarket A, the standard deviation for the wait time is 2 minutes. And at Supermarket B, the standard deviation for the wait time is 4 minutes. So because Supermarket B has a higher standard deviation, we know there's more variation in the wait times at Supermarket B. Overall, the wait times at Supermarket B are more spread out from the average, and the wait times at Supermarket A are more concentrated near the average. So just quickly before we move on, so you know that if you have a smaller standard deviation in this case, you're more likely to wait the mean amount of time, whereas if you have a larger standard deviation, you have more values all over the place. So to calculate the standard deviation, first we need to calculate the mean of the data set. Then we're going to take each data value and subtract the mean from that value. That is called the deviation. We're going to square that deviation for each data value that we have now subtracted the mean from. And then we're going to average those squared differences. That's called the variance. We're going to take the square root of the variance, and that is the standard deviation. We've basically come up with like a standard measure of how far away data is from the mean by doing all these subtractions, squaring, and then averaging and square rooting that number. So in a data set, there are as many deviations as there are items in the data set. The individual deviations are used to calculate the standard deviation. The deviations tell us how spread out the data are about the mean. So now I said that the standard deviation is always positive or zero, but like the individual ones, a positive individual deviation occurs when the data value is bigger than the mean, whereas a negative deviation occurs when the data value is less than the mean. So because of that, if you add up the deviations, you always get zero. And that's why we can't just do that to find something out about it. So by squaring each of those numbers, positive and negative, we make them all positive and the sum is positive. And that's just, we now can tell something from that. So if the numbers belong to a population, a deviation is x. X represents a data value minus mu, our population mean. But if we're working with sample data, the deviation is written as x minus x bar. And x bar is our sample mean. So we're going to do an example, and hopefully it helps sort of show what we're talking about. So you and your friends have just measured the heights of your dogs in millimeters, and the heights at the shoulders are 600 millimeters, 470 millimeters, 170 millimeters, 430 millimeters, and 300 millimeters. So the first thing we would do would be to calculate the mean of the data set. So that's the green line here. To do the mean, we would add up all of those heights and we would divide by the number of dogs, which is 5. So we get an average height, mu, and it's technically a sample, so it should be x bar, but this is our population, say. So our mean is 394 millimeters. Then we're going to take each of the individual dog heights and subtract 394 from those heights. So 206 is the difference between the tallest one and the mean, and then we have a deviation of 76. So here we have 600 minus 394, 206, 470 minus 394, 76. This is how we get all those individual deviations. And you can see we have some positive numbers and some negative numbers. And then the graph just shows you what it means by the deviation, the distance from that data value to the mean, either above or below. Now we're going to square each of those numbers. So remember, we had 206 was our first deviation, squared, that's 42,436. Square each deviation. Now even the negative ones are positive. Now we have a whole bunch of positive numbers. We're going to average those positive numbers. That is called our variance. So our variance is always a bigger number than our standard deviation. And in this case, if we add them all up and divide by 5, we get a variance of 21,704. So we're going to take the square root of the variance, and that is our standard deviation, the standard how far away a data value is from the mean. And in this case, when we do it, we get 147 rounded to the nearest millimeter. And in the graph, you can see that's this shaded region between the blue lines. So here's the green line is our mean, 394. We have one standard deviation above the mean and one standard deviation below the mean. That's what those two blue lines represent. And this just gives us a way to sort of say, like, what is normal? Which dogs are tall? Which dogs are short? So this guy, looks like a Rottweiler, is more than one standard deviation above the mean. And then our little Dachshund over here, he's more than one standard deviation below our mean. So I would say that the Rottweiler is tall or big, and the Dachshund is short or small in this data set. So we have this empirical rule. For data that is bell-shaped and symmetrical, so we've just recently talked about the shape of our data, the distributions. So for this kind of data, we are going to see a really helpful rule. Approximately 68% of our data is within one standard deviation of the mean. So that is the sort of the white area under this bell-shaped curve, we call it. 68.3% of our data falls within one standard deviation of the mean. Now remember, with our symmetric data, our mean and our median are going to be the same as our mode, so they're at that peak here. And you can see in this graph, it says mean, and then minus one standard deviation and plus one standard deviation. Oops, did not mean to jump ahead. Approximately 95% of the data is within two standard deviations of the mean. So that's the white data plus this light gray data. So that's a good portion of our data. 95.5% of our data is within 2 standard deviations of our mean. And then almost 100, 99.7% of our data is within 3 standard deviations of our mean. So that's the empirical rule. So we're going to do another example to calculate the standard deviation. And this is the following are the number of yards gained in NFL playoff games by rookie quarterbacks. And you can see the data there. We're going to do it in Excel, first by hand, and then we're going to compare it to the built-in formulas in Excel. You'll be happy to know Excel has those formulas. So if you go to our Excel sheet, Statistics 2.7, here are all of our yards gained by our rookie quarterbacks. Trying to make it a little bit bigger so it's easier to see. And the first thing we need to do, I put the instructions here, is calculate the mean. So down here, I'm going to do that average function. I'm going to highlight all of our data. And I get a mean of 159.6. So each deviation, you're going to take each data value and subtract 159.6 from it. So I'm going to use an equation, a formula. I'm going to do equals that cell, 193, minus. Now, if you go down here and you choose this cell, remember when we copy formulas down, it changes those cell references. So if you do it this way, put a $sign in front of the B and the 15. So now B is frozen and 15 is frozen. The B2, that will change. The column will stay the same, but the row will change because that's how we're moving our formula down. But the B15 will stay the same. So I'm going to hit enter. You could also, instead of doing that, just type in the number 159.6. When I do it this way, though, I can pull that formula down and Excel auto fills it in, and now I have each individual deviation calculated. So if you double click on it, you can see it's using 157 minus the 159.6, just like we want it to. All right, so we've calculated the mean, we've subtracted the mean from each data value. We're going to square each of those deviations. So there's a couple of different ways you can do a square. One way that's really kind of nice is I'm going to hit equals. I'm going to highlight the whole column. And then I'm going to use the caret, which is the symbol above 6 on my keyboard, and I'm going to type a 2. So that caret, that little sort of up pointing arrow, means raise it to the second power. And because I'm doing that whole column, I can highlight the whole column, type in the equation once, hit enter, and it fills it down for me. Now I can do it for that one row and then copy down just as well, like I did when I did the deviations. There's just multiple ways in Excel to do things, and so I want to show them to you so you are aware of them. So now I have all my squared deviations. I'm going to sum them up and divide by the number of data values that I have. I'm going to take the average of those. So I can take the average of my variations. Okay. That little hashtag, I wasn't entirely sure what was happening there. Again, I could sum these up. I could do a sum here, and then I could divide by how many that I have, or I can use that average function. And now the last thing to do is to take the square root of 1,786.04. And the square root formula is SQRT. Square root, and then what number do I want to take the square root of? That one. All right, so my standard deviation for the number of yards thrown by rookie quarterbacks is 42.26. That's how we did it by hand. Now in Excel, we have multiple formulas. The way I set this up, I have my Excel variance for the population and for the sample, and I have my Excel standard deviation for the population and the sample. So when you start typing in variance, you'll see a couple of things pop up. var.p calculates the variance based on the entire population. And then var.s would be the same thing on a sample. So we're just going to use all of them just to compare to the one we got by hand. So click on var p. Now I need to highlight my data. So I'm going to go up here. I'm actually going to use the Shift Control up arrow shortcut. I don't need all of that data. And I am going to hit parentheses. So look, I got exactly the same thing as I got when I did it by hand, because the by hand formula is assuming it's a population. When I do the sample variation, or variance, excuse me, I'm going to highlight the same data, but I get a slightly different number. It's bigger. And we're going to talk about the difference in a minute, about why it is different. So then the standard deviation, I have the variance now. I could square root those numbers to get the standard deviation, but Excel has a standard deviation formula for me, STD. And as you can see, again, we have a dot P for population. Highlight the data, 42.6, just like what I got by hand. And then there's also the dot S1. Highlight the data, and your parentheses, hit enter. I did the variance. That is not going to help us. Let's do the standard deviation for our sample. All right, it's a little bit bigger because our variance was a little bit bigger. So now we've done it by hand, and we've used the different formulas in Excel to calculate variance and standard deviation. So here we have that same information that we just did. And then what I did here was I put in a graph like the dog graph so you could see. So I did a column graph like we've done in Excel before. Each of these blue columns represents one of those data values for the quarterbacks. The red line here is the mean that we calculated in Excel. And then the green line is approximately one standard deviation above the mean and one standard deviation below the mean. And that, I just wanted to put that in so that we could, again, like we did with the dog, say, oh, look, this quarterback, he threw more than one standard deviation above the mean, okay? This quarterback threw less than one standard deviation below the mean. Now, depending on what your data is, I would think that above the mean, would be what we were looking for, or what would be beneficial as a quarterback. So it's just one way to look at our data and say what seems normal, what seems out of the ordinary. And again, 68% of our data approximately is going to be within a standard deviation above and below that mean, the red line. So I had jumped ahead. We've already done the calculations using the Excel commands. So again, the population one, this is what the formula looks like when we write it out. Here is our X, our data value, minus our population mean, our mu. Remember what all this stuff means. This is the deviation. We square it, and we sum up all of those squared deviations, divide by the total number of data points we have, and then take the square root. So that's what we did when we calculated it by hand. But if you are using sample data, then what you really should divide by is n minus 1. And it's one less than the number of data values in our sample. This is what it looks like written out in formulas. So our data value minus x bar, which is the sample mean. Those subtractions, those differences are our individual variations. Square them, add them together. That's what the sigma stands for. Divide by n minus 1, take the square root. So S is the value, the symbol, the letter we use for the sample standard deviation. Sigma is the Greek letter, small lowercase s, that we use for population standard deviation. And now we would have gone back to Excel to do those formulas, and you can see that the way we were doing it, we were treating it like a population, even though those five, not the dogs, sorry, the quarterbacks were just a sample of quarterbacks. So we really want to use the sample one when we're in Excel, just like we're using the .exe for quartiles and percentiles so that we can be consistent. We're going to use the sample, variance, and standard deviation formulas. But you should know that both exist and how they're calculated so that if you ever do other statistical work, you know which one is which and what you're looking at. So a couple of notes. The variance is a squared measure, and it doesn't have the same units as our data. So taking the square root solves that problem, and the standard deviation measures the spread in the same units as our data. For the sample variance, we divide by that sample size minus 1, n minus 1, and the sample variance is an estimate of the population. And dividing by n minus 1 actually gives a better estimate of the population variance than dividing by our sample size. So we are going to do another example. Here's a picture, oh, by the way, of our Boston Red Sox celebrating their win over the Tampa Bay Rays, but that was back in 2001. So maybe we'll just move on and not talk about that. But here are some ages, not of our Red Sox in 2021, but the ages of each of the players are as follows. Let's go back to the Excel sheet, and we're going to do the mean, the variance, and the standard deviation of the data sets. Then we want to find the value that is 2 standard deviations above the mean. Remember, the empirical rule tells us that about 95% of our data, a little bit more, lies usually within 2 standard deviations from our mean. So I'm going to go over to our ages tab. Here does all of the data over here on the side. And I'm going to calculate the mean. So this is average. I'm going to click on the first one, do Control-Shift down arrow, end my parentheses and hit enter. So the mean age, the average age is 30.68. Now we're going to do the population variance, like if we were assuming this was the whole population. So variance var.p, highlight my data, enter, and I'm going to do the standard deviations. So standard dev.p, highlight my data, and my parentheses, and I get a population standard deviation of 5.97. Now we're going to do the same formulas, but we're going to use the sample formulas. So this is equal to VAR now dot S. Same thing, highlight the data, end my parentheses. Same thing with the standard deviation. And we're going to do the sample one, so it's the dot S. Highlight my data. Be careful when you're highlighting your data. It's easy to make a mistake, especially when you're doing multiple formulas and commands. So just be careful. So now we have all this information, and we want, what is the value that is 2 standard deviations above our mean? Well, if we use the population standard deviation, both of these are going to start out with equals our mean plus 2 times whichever standard deviation we're using, okay? So mean plus 2 times that standard deviation. So the value 42.62 is 2 standard deviations above our mean of 30.68. Now, if we use the sample standard deviation, so equals our mean plus, because we want above our mean, 2 times the sample standard deviation. Sample standard deviation is a little bit bigger, so 2 standard deviations above our mean is going to be bigger, and it's 42.87. Not a huge difference, but it is a difference. So just looking at our data, you can see over here there's a 31, so the mean is actually like right between those 2 numbers. So anyone over 42.62 or 87 would be 2 standard deviations above that mean. And you can see in our data we don't have anybody of that age. Here's that same information again. And so a few more notes. The standard deviation, S for our sample standard deviation, or sigma for our population standard deviation, is either 0 or larger than 0. So it's always 0 or positive. When we describe the data with reference to the spread, we're talking about variability. The variability in data depends upon the method by which the outcomes are obtained. So for example, by measuring or by random sampling. When the standard deviation is 0, there is no spread. That is, all the data values are equal. Doesn't happen very often, but it's a possibility. The standard deviation is small when the data are all concentrated close to the mean, and it's larger when the data values show more variation from the mean. And the outliers can make our sigma or our S value very large. So just keep that in mind because they are more spread out from the mean. In symmetrical distributions, the standard deviation can be very helpful, but in skewed distributions, the standard deviation might not be as much help because two sides of a skewed distribution have different spreads. So with skewed distributions, you might want to look at the 5-number summary, the min, Q1, median, Q3, and max. Graphing your data can help you get a better feel for the variation in the data. You can show your data in a histogram or a box plot, and that will show if it is symmetric, where the standard deviation would be helpful, or not, if it was skewed. We're going to look at an example with graphing. So the following data are the first exam scores from Susan Dean's spring pre-calculus class. We're going to calculate the following to 1 decimal place: the sample mean, the sample standard deviation, the 5-number summary, the interquartile range, the IQR. We're going to do a box plot and a histogram with 5 bins of width 15. And we're going to do a chart with the data, the frequencies, the relative frequency. We're going to do a frequency chart, frequency table, and cumulative relative frequencies. We're going to use percents rounded to 1 decimal place. Up ahead of ourselves. So if we go back to Excel and we go to our grades tab, so much of the stuff now Excel is doing for us, right? So our sample mean, so equals average, click on your first piece of data, Control Shift down arrow, end your parentheses, you have your mean. Sample standard deviation, so equals STDEV sample, so dot S. Highlight your data, end your parentheses, and hit enter. So my sample standard deviation is 17.92. The minimum, this data is ordered as I look through it. I can see the lowest value and I can see the max value, but if I want to use, if it wasn't ordered, or if I want to use the command, it's the min command. So it's A2 to A32. So I haven't done this very often, but I can just type those numbers in. So quartile.exe, my data I just said was column A, row 2, I use a colon, to column A, row 32. And then you can see over on the side, it's highlighted it for me. So, some people like using a keyboard, some people like a mouse, the trackpad. There's just lots of different ways to do it. So we're looking for quartile 1, so I'm going to type in a 1, hit my parentheses, and hit enter. So Q1 is the value 61. 25% of my data is less than or up to, and maybe including 61. The median, A2 to A32, 72. So my sample mean is a little bit higher than my median. Q3, so quartile.exe from column A, row 2, all the way to column A, row 32. Quartile 3, so I'm going to type a 3 in here. So 75% of my data is below 90, and 25% is 90 or above. And then my max, again, I could just look at it because it's ordered, or I can use the maximum function, A2 to A32. So remember the interquartile range is Q3 minus Q1. So I'm just going to click, I'm going to do my equal sign, Q3 minus Q1, and I have an interquartile range of 29. 50% of my data is between my Q1 and my Q3. We talked about range a little bit at the beginning, and that's the max minus the min, but in this time we wanted the IQR. All right, we're going to do a box plot. So highlight your data. Remember how to do this? We're going to go up to Insert. We're going to do a box and whisker plot. I'm going to move it over, and I'm going to just make it a little bit smaller. My chart title, this was first exam scores. So exam scores. And remember, when you right-click on the blue box, you can add your data labels, and then you can see how it lines up with the information that you calculated using the Excel commands. The histogram, remember, same thing. We're going to, our data, well, see if I click over here, our data will stop being highlighted. So highlight your data again. We're going to insert a histogram this time. You can see I already have the table typed in, but we're going to choose the histogram. I did put a little space up above for it, but let's keep it here next to the frequency table. And we said on the slide to have 5 bins of width 15. So we're going to right-click on the blue. We're going to format our data series. We're not going to do that. We're going to right-click on our axis, our horizontal axis, and we're going to click on bin width. And we're going to type 15, and that does change our number of bins to 5, so that's perfect. Chart title is, again, exam grades. Remember, when we're doing histograms in Excel, sometimes it's easier to do the histogram first and then build the frequency table. So over here when I have this grades column, I took the numbers from the histogram. So I can just see what the frequencies are, but don't forget, I can also add my data labels if it's hard to read the numbers off of it. So the frequency for the first interval, 33 to 48, is 2. 48 to 63 is 7. 63 to 78 is 9. 78 to 93 is also 7. And 93 to 108 is 6. What's our total? I'm going to sum up those frequencies. Often you already know that information, but we have 31 grades here. So the relative frequency, remember, we take each individual frequency, so 2, and divide by that 31. So if I pull it down, it calculates it for me. I said on the slide to use, in the chart, use decimals rounded to one place. So these guys are already highlighted because I just filled them down. I'm going to go up here and click on %, and I'm going to increase my number of decimals. Remember that cumulative relative frequency starts out by being the same. The first one is the first relative frequency, but then each subsequent one, we're going to add the one that came before. So equals 6.5 plus the new one, 22.6. And then when I pull that down, it adds 29.0 plus 29.0. Just happens to be the same. Pull it all the way down, it should end up adding to 100% or a 1 if it wasn't already in percents, so that I know that I got all of my data. Okay, so here I have my sample mean and my standard deviation. I have my 5-number summary and my IQR. I have a box plot that shows the spread of my data in one way. And here's my histogram and my frequency table displaying my data in another way. And here it is again. So when we're comparing values from different data sets, the standard deviation can be really useful in this situation. If the data sets have different means and standard deviations, then comparing the data values directly can be misleading. So for each data value, we want to calculate how many standard deviations it is away from its mean of its data set. We're going to use the formula where the value equals the mean plus the number of standard deviations times the standard deviation. So remember we were talking about like 2 standard deviations above, we took the mean and we did 2 times the standard deviation. That gave us the value that was 2 standard deviations above the mean. So if we solve that little equation for the number of standard deviations, you get the value minus the mean divided by the standard deviation. So if I knew the value and I was like, how many standard deviations is it away from the mean? This is the formula I would use that would give me a number and tell me that. And then I can compare that for these different data sets, the data from different data sets, to see how far away from their mean they are. So that number, how far away from your standard deviation you are, is called your z-score, and we use the symbol z. In symbols, it looks like this, where our data value x equals our mean plus our z-score times our standard deviation. Or if we're trying to find the z-score, we take our value minus our mean and divide by the standard deviation. This row here, I'm just solving for z from this formula. And then we have our population row, which is pretty much the same, but we use the population mean and the population standard deviation in both of these 2 formulas. So our example here, we have 2 students, John and Ali, from different high schools, and they wanted to find out who had the highest GPA when compared to his school. So we're going to use the standard deviation to figure this out. So John's GPA was 2.85, his school mean GPA was 3.0, and his school standard deviation was 0.7. Ali's GPA was 77, his school mean GPA was 80, and his school standard deviation was 10. So see, they were done on different scales, and so you can't just compare them directly. So with the data that we have, what we can do is calculate the z-score for each of these GPAs. We're going to use the formula data value minus the mean divided by the standard deviation. So John, he had a 2.85 minus his GPA, his school GPA of 3.0 divided by the standard deviation. His z-score was negative 0.21. That meant he was 0.21 standard deviations below his school's mean GPA. Ali his GPA was 77 minus 80 divided by 10. His school's mean GPA and school standard deviation. And he got a z-score of negative 0.3, also below the school's mean GPA. So in this situation, John has the better GPA when compared to his school because his GPA, though they're both below their individual school mean GPAs, Ali's GPA is more below than John's is. So everything is dependent on the context that you're looking at it in. Another example, 2 swimmers, Angie and Beth from different teams, wanted to find out who had the fastest time for the 50-meter freestyle when compared to her team. Which swimmer had the fastest time compared to her team? So Angie had a time of 26.2 seconds, and her team had a mean time of 27.2 seconds, and a team standard deviation of 0.8 seconds. Beth had a time of 27.3 seconds, but her team had a mean time of 30.1 seconds and a team standard deviation of 1.4. So we're going to figure out each z-score and then compare them. So Angie, again, take her time, 26.2, subtract her team mean time, 27.2, divide by her team standard deviation, 0.8. She has a z-score of negative 1.25. Beth, similarly, we take her time, 27.3, subtract her team mean time, 30.1, and divide by Beth's team's standard deviation of 1.4. Beth has a z-score of negative 2. So Beth has a better time compared to her team because her time is 2 standard deviations below her team's mean, and lower times are better in a race. So in the GPA, you don't want to be more below your mean, but for swim times, race times, you do. So Beth has the better time compared to her team's mean time. That's what it means when you're comparing z-scores. You're comparing them to those separate means and sample sets. So in section 2.5, we saw that when we only have a frequency table, we do not know, and we do not know individual data values. We can't find the exact mean, median, or mode, but we can find an estimate of the mean of the group table with that formula. Remember that had the sigma notation. You take your frequency times the midpoint of your interval, add those all up, and then divide by the sum of the frequencies to get the mean of the frequency table. So we can do something similar here when we only have a frequency table and not individual data, and we want to have an estimate of the standard deviation. So it's going to be very similar to both the mean of the frequency table formula and the standard deviation formula. We're going to figure out the midpoint. We're going to subtract the sample mean from it. We're going to square those individual deviations. But then we're going to multiply them by the frequency of that interval, just like we did up here, divide by n minus 1, and take the square root. So here's our frequency table. We're going to use this formula, and we have to do multiple steps here to figure this out. I didn't write the steps in here. So let's go over to the Excel sheet. The last tab is our grouped data. That's because I put it in here. And you can see we have our intervals and our frequencies. So the first thing we're going to do is we're going to calculate our midpoint. Remember, the midpoint formula says take the endpoints, in this case 0, add it to the other endpoint 2, divide by 2. In this case, you knew it was going to be 1. And maybe in, like I said before, you might be able to just kind of see them, what the midpoints are. The middle of 3 and 5 is going to be 4. But if you did it by the formula, you would do parentheses 3 plus 5 divided by 2. Make sure you parenthesize that as that sum, the addition piece, or you'll get something that's off. And then you can just keep going down and filling those in. Remember, you can't pull this one down because you're not using cell references. I made a mistake, and Excel gave me a good correction for it, so that was fine. I accepted that. So now I have all my midpoints of my intervals. The next step, I am going to I'm doing this. I was like, why am I doing this piece here? I have to figure out the grouped mean first. I don't even know the mean. So I have to do my frequency times my midpoint. So do the frequency times the midpoint. This one I can pull down. And then what I'm going to do is I need the total of my frequencies. And I need the sum of F times M. So I'm going to go back here to show you. This is what I'm doing right now, the mean of the frequency table first. So my grouped mean is going to be 197 divided by 26. And I'm just typing the numbers in here because I want this grouped mean to stay the same for each of those intervals, okay? And I'm doing it this way because now I can take my midpoint, in this case 1 on this row, and subtract the mean from it. So equals the midpoint minus the grouped mean. And it's obviously negative. I can drag that down to autofill all of those. M minus the grouped mean. So going back to the slides, we're using this formula. M is my midpoint minus my sample mean. The next thing I'm going to do is square each of those numbers. So remember, I can do equal my deviation, highlight the whole column, and use the caret 2. And each one of those will get squared. And then I'm going to take my frequency times that number. So equals my, go back to frequency. Be careful here because we have so many columns now. You don't want to pick the wrong one. And then you're going to multiply that by the squared value. And you can drag that down and have Excel autofill it for you. Boy, that's a lot. So let's look at what we've done. We've done this whole numerator here. We found the midpoint. We subtracted the grouped mean from it. We squared those deviations. We multiplied each deviation by the frequency, and then we added them all up. Maybe we didn't do that part. Let's do that here. So equals the sum of all of those squared deviations. So the final step is to divide by n minus 1. So that's 1 less than the number of data values we have, and then we're going to take the square root of that. So you can do it in multiple steps. You can say, okay, well, this number, I want to divide that number by n minus 1. Well, n is 26. I have 26 data values minus 1. Okay, no, that's just 25. I want to type that in. This is my variance. So now for my standard deviation, remember I'm going to take the square root of that number. And I get a standard deviation for my grouped frequency table of 3.5. So this might be the biggest and the most work that we've had to do for any of the things that we've seen so far in this class. And we're not going to do it that often, but know when you don't have the individual data values, if you need an estimate of your mean or an estimate of your standard deviation, this is what you have to do, all of these columns, okay? So here's our standard deviation for our grouped frequency table, which it didn't tell us what the data represented, but for each of these intervals and frequencies, we found that we had a standard deviation of 3.5. So that is the end of a very long section, section 2.7 on measures of the spread of data.